This software supports complex fluid phase behavior and asphaltene precipitation studies in oil and gas development. It is a platform for phase behavior simulation, evaluation, and experimental data import. It covers PVT thermodynamic analysis, asphaltene precipitation calculation, and experimental data processing. It also includes chart-based evaluation and risk assessment for reservoir, wellbore, and surface nodes. The platform integrates AI algorithms and evaluates common physical and chemical treatment methods. Its goal is to make asphaltene risk assessment faster and easier to apply outside the laboratory. It also reduces the high cost of sensitivity studies under controlled experimental conditions. The result is quantitative risk evaluation with visual risk classes for each production node. After launch, the interface uses 3 columns, the menu tree on the left. The output area is in the center, and parameter inputs are on the right. First, create a project. In the dialog, select the target path. Enter the project name, oil sample name, and description. These details are saved into the project data file, and the system uses the selected path. It automatically creates a project folder with an APX file and an oil sample data folder. That folder stores all data files generated during later analysis. Experienced engineers can edit the data files directly to adjust the calculation workflow. The software follows common reservoir simulation data structures and stores each module separately. This improves data management. The data files use a keyword-style format common in petroleum software. After the project is created, enter the basic information first. This includes the unit system and the fluid type. Users may choose standard units or define custom units for parameters. Then enter key values, such as reservoir temperature and pressure. Units are mapped automatically. After clicking Apply, these values are sent to all later modules, reducing repeated input. The design follows one-time input and full workflow reuse, while preserving sample details. Those records are available for other users and engineers. Next is PVT experimental data import. 9 types of experimental data modules are preset for import. Users select the experiment type needed for the current task, such as asphaltene analysis. For that analysis, SARA data are required. Add an experiment, then choose File Import or Manual Input in the Import page. For file import, select the source file and the target sheet. The software identifies required columns. Users can still adjust the mapping and preview the file on the left. After confirming the import settings, add the selected data into the software. Users may also specify header and data rows manually before preparing later calculations. Additional SARA component information can also be entered. A bubble point pressure experimental dataset can be added as well. After basic data import, the thermodynamic section provides 3 common EOS models. They are PR-EOS, PC-SAFT, and CPA. Right-click to add PVT tasks. Add phase behavior analysis, sensitivity analysis, or experimental fitting. First, import oil components. Select target components from the library, then import them. Next, enter pure component composition information. Components can be split by choosing the starting carbon number. Also set the number of split components, correlation method, and other required parameters. After splitting, pseudo-components are added to the component table. If duplicates exist, use copy and paste. The buttons in the right side input panel provide the same functions. After entering components, mole fractions, and KIGE values, enter temperature and pressure. These temperature and pressure values already come from basic information, so calculation can start directly. The calculation returns the bubble point pressure. It also returns the mole fractions of components in each phase. Besides single-point calculation, pressure scanning is supported. By setting the scan type and range, users calculate trends under different pressures. The EOS results also support sensitivity analysis. This section identifies which parameters have the largest influence on the target result. Select multiple parameters and click to draw a tornado chart showing the strongest effects. This prepares sensitivity analysis and fitting while reducing blind trial and error. By default, only recommended adjustable parameters are enabled. Some parameters are locked. Users can right-click to release all parameters and use them as adjustable variables. The right-click menu also supports clear and reset operations for selected component or KIGE parameters. After selection, define the upper and lower search ranges. Then click Apply to generate the orthogonal experiment table. This avoids an explosion in case count when many parameters are selected. Each case represents one modified parameter set and value combination. After calculation, the center output area shows the result table and response trends for each case. Experimental fitting compensates for thermodynamic model input errors and improves agreement with real data. Because bubble point data were imported earlier, the bubble point target can be selected here. Select the specified bubble point pressure target. As in sensitivity analysis, choose component and KIGE parameters for fitting. Set the search range. Experienced users can also choose the optimization method. Here, the software shows fast, balanced, and precise calculation modes. After the optimization target is selected, the background model is chosen and run automatically. In the center plot, the calculated result gradually approaches the experimental value. When the fit is good enough, users can stop and keep the latest iteration result. If the fitted parameters are not satisfactory, fix the current values and repeat fitting. This gradually matches the experimental target and avoids blind parameter searches. It reduces exponential growth in computation. PC-SAFT is also a common phase behavior model. It is suitable for heavy oils. After composition input, bubble point, and two-phase results are calculated.